If you were to take a microscopic cross-section of NASA's most expensive thermal protection shield, you would discover an invisible flaw, a defect that cost American taxpayers over $2 billion to confirm. It sits directly at the atomic boundary where heat meets cold, a tiny structural shear that appears only under zero gravity and high radiation, for nearly 30 years. Aerospace engineers in Houston believed this microscopic failure point was an unalterable law of physics. They called it the ultimate wall of space hardware, a physical boundary so brutal that America's most ambitious deep space projects were quietly pushed into dusty archives. NASA's top minds concluded that no material forged on Earth could continuously transfer massive thermal energy across a vacuum without degrading, fracturing, or destroying itself from the inside out. And yet, thousands of miles away, inside a secured facility in Shanghai, a team of engineers built a hardware component that looks almost disturbingly simple. When Western intelligence analysts first examined the telemetry data from a recent Asian orbital test, they didn't see a complex military weapon. They saw a simple metallic core, performing a function that every Western textbook declared mathematically impossible. To understand why this single piece of hardware is sending shockwaves through the aerospace industry, we have to disassemble the original American failure piece by piece. Inside every high-powered satellite, deep space probe, or hypersonic vehicle, heat is the ultimate killer. Earthbound electronics rely on air or liquid cooling systems to flush away excess thermal energy. In space, there is no air, there is only a pure, cold, relentless vacuum. If you run a high-performance computer, an advanced radar, or a laser transceiver in orbit, the heat has nowhere to go. It builds up inside the housing, warping silicon chips, melting solder joints, and short-circuiting multi-million-dollar instruments within minutes. In the late 1990s, NASA launched a top-secret initiative to solve this exact bottleneck. Their idea was brilliant. Use liquid metal alloys flowing through microscopic channels to suck heat away from sensitive electronics at lightning speed. They built intricate heat exchangers out of titanium, filled them with high-density liquid metal, and placed them inside extreme pressure chambers. On the ground, during static testing, the performance was breathtaking. The system cooled high-powered processors better than anything built in human history. Engineers celebrated what they believed was a historic breakthrough, but then came the orbit simulation trials. When the prototype was subjected to microgravity and rapid thermal cycling, the liquid metal began to behave like a destructive fluid weapon. At high velocities, tiny microscopic bubbles formed within the metal alloy. In a normal gravity environment, these bubbles rise to the top and dissipate harmlessly. In space, without gravity to pull the heavier liquid downward, the bubbles clustered together, creating violent microimplosions along the internal walls of the pipe. It was a phenomenon known as cavitation erosion, and it destroyed NASA's titanium hardware in less than 48 hours of continuous operation. Engineers tried everything: re-engineering the pipe walls, changing fluid pressure, adding exotic synthetic coatings. Nothing worked. Every single modification failed in the exact same spot. Right at the junction where liquid metal made contact with solid housing, the American Space Agency faced a brutal realization: liquid metal cooling under high pressure was a dead end. In 2006, the program was officially scrapped, its data classified, and the scientific consensus was locked in place. The physics simply wouldn't allow it. Or, at least, that is what the Western scientific world believed for nearly 2 decades. While Washington moved on to less risky, less efficient cooling alternatives, a silent shift was happening across the Pacific, excluded from international space agreements. Chinese aerospace researchers were building their own technical roadmap from scratch. They didn't have access to NASA's classified failure reports, which meant they didn't know the problem was supposed to be impossible. When Chinese researchers began studying liquid thermal dynamics in the early 2010s, they stumbled onto the exact same erosion wall that had halted NASA. Their early prototypes corroded, cracked, and failed just like the American models. At that point, any standard engineering team would have abandoned the effort, following the established global consensus. Instead, someone made an unexpected decision that changed the trajectory of the entire project. Rather than trying to stop the liquid metal from eroding the pipe walls, they asked a radically different question: what if the pipe wall could heal itself while operating? It sounded like science fiction. But it led to a 10-year research campaign hidden deep within academic metallurgy papers. Engineers began experimenting with a unique composite material, layering microscopic graphene sheets into a flexible liquid alloy mesh. Graphene, an atom-thick lattice of carbon, is incredibly strong, lighter than paper, and capable of conducting heat faster than almost any known material. By suspending graphene layers within the liquid metal matrix, they created a fluid that wasn't just a coolant, but a structural protection agent. When microbubbles form and implode inside the channel, the suspended carbon layers automatically migrate toward the point of pressure loss, instantly sealing microfractures before they can expand. The fluid itself was repairing the hardware while it ran. For years, Western space agencies watched Chinese scientific publications without paying much attention. To most observers, these papers looked like abstract laboratory experiments, far removed from real-world aerospace applications. That was a catastrophic miscalculation. Behind closed doors, the lab demonstrations were rapidly transitioning into industrial manufacturing. By 2021, high-precision fabrication plants were producing modular cooling plates integrated with this self-healing liquid metal matrix. They had solved the cavitation problem, not by making the metal container stronger, but by making the fluid smarter. Yet, proving a material works in a laboratory is one thing. Proving it can survive the brutal environment of space is another story entirely. In late 2023, an unannounced satellite launched into low Earth orbit from a facility in the Gobi Desert. Official mission manifests described the satellite as an experimental communications testbed. In reality, it was carrying the completed, miniaturized thermal control unit that NASA had abandoned 20 years earlier. Space tracking networks in the West monitored the object as it achieved stable orbit. For the first few weeks, everything appeared normal. Then, ground telemetry receivers picked up something that made defense analysts rub their eyes in disbelief. The satellite was drawing power at levels that should have been physically impossible for an object of its size. It was emitting massive radio frequency signals, running dense computational loads, and generating thermal output that would normally melt an ordinary payload within hours. Sensors on Western tracking arrays waited for the spacecraft to fail, expecting the onboard systems to cook themselves in their own heat. Hours turned into days turned into weeks, and weeks turned into months. The satellite didn't overheat. Its internal temperature readings remained rock solid, perfectly stable, sitting well within safe operational limits. The self-healing liquid cooling loop was operating flawlessly in the vacuum of space. China hadn't just matched American technology, they had leapfrogged an entire generation of space hardware design. To understand why this moment marks a historic turning point, you have to look at what this single component unlocked in modern space warfare and satellite communications. Power is everything. If you want to track hypersonic missiles, transmit vast amounts of encrypted data, or jam enemy communications, you need immense electric power. Immense electric power produces immense heat, for decades. The primary bottleneck limiting satellite performance wasn't battery capacity or computer speed, it was heat dissipation. By solving the thermal problem, China effectively removed the leash on space-based computing power. A satellite equipped with this new liquid metal system can run high-powered radar arrays continuously, night and day, without needing massive, vulnerable radiator panels that can be targeted by anti-satellite weapons. It allows compact, lightweight satellites to perform tasks that previously required massive space platforms costing billions of dollars. The balance of orbital hardware capability shifted, not through a massive military buildup, but through a single, microscopic breakthrough in fluid mechanics. When news of the successful orbital test finally trickled through defense intelligence channels, it sent shockwaves through the American defense establishment. Engineers in Houston and Washington realized they were no longer setting the pace of space innovation. The very problem NASA declared unsolvable had been solved by an opponent using a philosophy Western scientists had dismissed as unworkable. Now, Western aerospace giants are scrambling to restart their own liquid metal research programs. Engineers are digging up old files from the late 90s, trying to re-engineer what was discarded 2 decades ago. But reversing 20 years of momentum isn't easy. Building the supply chains, mastering the advanced carbon manufacturing, and running the testing iterations will take years, if not a full decade. In the fast-moving landscape of modern space technology, falling 10 years behind is an eternity, and while Western labs try to recreate what was lost, the engineers in Shanghai aren't standing still. They are already integrating this self-healing technology into deep space probes, lunar infrastructure designs, and high-orbit defense platforms. The breakthrough that started as a small liquid metal experiment is now becoming the foundational backbone of an entire space empire. The lesson hidden inside this story isn't just about space hardware or thermal dynamics. It's about the danger of assuming that a scientific barrier is permanent simply because you failed to break it. NASA looked at the physical limits of liquid metal in 2004 and decided the problem was impossible. China looked at the exact same limits, accepted that the old rules didn't work, and wrote an entirely new chapter in material science. As dozens of these next-generation payloads glide silently across the night sky, one terrifying reality remains clear. The technology that was supposed to keep America miles ahead in space was left sitting in an old folder, waiting for someone else to open it, and as new signals stream down from orbit, the rest of the world is left wondering what other impossible problems have already been solved in the dark.